All right, time to start. So, yeah, if you take speech classes, they always tell you like, don't say you hate the topic, and I'm breaking all the rules, right? Because I mean, stoichiometry is important. It's kind of boring, you know. So, I mean, you're probably thinking like, why did this guy, go through 4 years of college to go through another 4.5 years of grad school to get a PhD in this stuff? So, and hopefully, and I'm excited about today. Hopefully, you'll start seeing some of the stuff that I think is cool. So, and I think quantum is cool. It's magical. It's like actually when I was in grad school, this is also when Harry Potter came out, and well, at least up to book 4 when I entered grad school, and I remember I was studying quantum, and I was like, this stuff makes no sense, and I started reading Harry Potter, and I feel better now because it's weird. It's really weird. So, and oh, by the way, this stuff today we're talking about is not on the test. This upcoming test due today, and if anyone has any issues or anything, just let me know. So the tests and whatnot. But no, it is not a physics class, but a lot of times we talk about things like mechanics. It's known as classical physics. So classical mechanics is classical mechanics, right? So like gravity. So my center of mass is here, pushing down with about 262 pounds. I've been losing weight. And although it might be 265 with all my clothes on. So then, oh, sorry about that image, by the way. But then the floor pushes back with equal opposite force, right? So vectors cancel. And things like me tossing my water bottle around. This is all classical mechanics stuff, friction. I guess mechanics still. So now we're talking about quantum mechanics, which is a little stranger. And I might ask you, which door did you come in today? And probably everyone here is like, that one, right? Because among other things, we're all pretty large. Average mass of a human is around 70 kilograms. So, and that's big. An electron, for instance, is 9 times 10 to the minus 31 kilograms. So it's really small. If we were electrons and I asked you, like, what door did you come in today? You'd be like, that's a stupid question. We came in both doors at the same time. And like, I kind of just moved through the wall. I didn't even have to come in the door. I tunneled in here, So there's a very different type of things that happen in quantum mechanics. And one of them, which I'm kind of alluded to there, is something called uncertainty in position and momentum. We'll talk about that, probably not this class, but next. And maybe you've heard of Schrodinger's cat before. So well, I guess backing up, there's, scientists are kind of, I don't know how many scientists, some of them are, there's almost like artists in a way. There's some that are like really cool, really chill, and some are just horrible people. There's a lot of scientists that if I ever met them, I would really like to punch them in the face. So Heisenberg is one, Haber is another one. They're just terrible people. But Schrodinger, on the other hand, Schrodinger, maybe one of those people, you ever ask that question, like, 4 people, living or dead, you want to have lunch with, or something like that. Who would it be? Schrodinger would make my top 10 list. He was a very interesting person. And he also, if you ever go to Stockholm, Sweden, there's the Nobel Museum there, and each Nobel laureate, they get a couple minute spiel. And there was just something about Schrodinger. He just had this electrifying voice when he was talking. It was very alluring. And he actually had a wife and a mistress too. So he was, more alluring in other ways. So Schrodinger was a physicist, and he studied waves. And there was a conference that they were talking about the hydrogen atom, and they were talking about all the observations. And Schrodinger allegedly spent the weekend away with his mistress somewhere and came back and came up with Schrodinger's wave equation. So, and that was his inspiration apparently. But as he was studying this, if you want to know what Schrodinger's cat is, So there's something called a superposition. So we'll talk about electrons can be spin up or spin down. And if you have a single electron, it can be spin up or spin down, but actually it can kind of be both at the same time. And that's called a superposition. So with Schrodinger's cat, he goes, I have a cat that's in a box, and it's this superposition stuff is if I open up the box, then there might be this hammer that hits a vial of cyanide and kills the cat. So, but it's not certain if the box is if it's gonna trigger that mechanism or not. So I only can tell if I have a live cat. I'll open the box. It'll operate the mechanism. It's either going to be a live cat or a dead cat. But I can only tell when I open the box. But what happens when the box is closed? Like then I have this cat that's somewhere between living and dead. It's kind of a weird way to describe superposition, but I guess, this is the 1930s, I mean, I guess we had fewer things to reference back then. Although I approve of the cat analogy, but a little weird. So that's Schrodinger's cat. And we won't talk too much about, I just mentioned superpositions. We're not going to, that's kind of above and beyond this class. But this is the cool stuff though. So like I said, I'm really excited to talk about this stuff because it's cool. So, and tunneling, that's another thing we'll talk about. Well, I guess we will talk about that. We'll talk about that a little later. Not necessarily tunneling, but uncertainty. So let's talk about some other things. Electromagnetic radiation. So we'll talk about the spectrum in a second. So what is electromagnetic radiation? It is a transverse wave. A transverse wave is a wave that the displacement is proportional to the motion. Okay, so what does that mean? So ocean waves, they're transverse waves, right? So when you have an ocean wave, the wave moves this way. What way does the water go? Right? So the wave is moving this way, and then the water, so if you're sitting here in a wave, you're kind of going like this, but the wave is moving this way. So an ocean wave, of course, we will see it move this displacement and alongside the wave moving. So what electromagnetic radiation is, it is an oscillating magnetic and electronic field. And I know this is not a physics class. The electronic field is kind of like gravity in a way. It gives potential between charges or repulsion. And magnetic fields, they make things spin. So very grossly oversimplification. But in a like light and other radiation, so if the wave is moving this way, the electronic field is moving this way, up and down, and then the magnetic field is moving this way. So perpendicular. Well, I guess it's just whatever. Perpendicular, but then wave is moving this way. So we have three dimensions, right? So motion of the wave, electronic field, magnetic field, both perpendicular to each other. So, and to the motion. So it's like a double oscillating wave. So, questions so far? And then there's some simple things with waves. So, and we're not going to go all the way into wave mechanics, but here is a wave. And a couple of features of the wave. You have the height of the wave, and the height is called the amplitude. It's also how strong the wave is, right? So it's more fun to surf in a 50-foot wave, depending on your skill level, than a 2-foot wave, right? Because the 50-foot wave has more energy, surprise, surprise. So that's one of the ways that waves have more energy, is a higher amplitude. And then the length of the wave is called the wavelength. You can measure it from the crest, the top of the wave, crest to crest, the bottom, the trough to the trough, or you can measure it from start to finish. So it goes up. Okay, so you can call this the wavelength, the top the wavelength, and the bottom the wavelength, whatever suits your fancy. So and other things, colors, which we'll go to soon. Colors are different wavelengths. If you can't see this, red is the top, yellow is the middle, and blue is the bottom. So There's also something called frequency. But anyways, so you can see the red line, the red band on the top. It has a longer wavelength. So the wavelength is longer, and then the frequency is lower. So frequency just means number of times something happens. Like, what is your frequency of eating? So, I mean, for me, it's usually 3 meals a day, maybe 2 or 3 snacks, depending, right? So that's my frequency of eating, 3 to 5-ish times a day. So you notice that I'm giving a number and a cycle. Frequency, we typically use hertz, which is 1/seconds, so inverse seconds, number of times per second. So that's red light, and yellow is medium, and then we have blue light here. So it has a shorter wavelength. The wavelength, you can see that zoom. So shorter wavelength, but a higher frequency. So question, which boat, here's my chemistry level art skills. So which boat is going to have a rougher time? Is it going to be the red boat on the top or the blue boat on the bottom? There's a storm coming. Which one has the oh shucks factor? What's that? So it's something. Oh, I couldn't hear. No one wants to play. Blue boat, yes. Blue boat is in more dire straits. And because there's more energy in the system, you can probably tell there's more energy here. The same thing happens with light. So we'll talk about this coming up. The higher the frequency, the higher the energy. So, and you can, and it just, I can almost do this without proof. It makes sense, right? Higher frequency means higher energy. So, and this is where chemistry is weird. Where everyone else, this is probably because I think the Germans started this. Germany used to be the most advanced scientific country in the world. Now it's America. Well, Germany's pretty close behind, to be honest with you. So if it was discovered here or developed here in the States, we would probably call wavelength L and frequency F, right? But we don't do that. For wavelength, we use the lowercase lambda. That's the Greek letter lambda. This is capital lambda, that's lower lambda. And then there's capital nu and lower nu. So frequency is the funny V, it's the Greek symbol, the Greek letter nu, GNU. So, just hopefully this makes sense. This equation here, wavelength lambda times frequency equals speed. So how long the wavelength is and how many times it happens. So that's distance over time. That's speed. So, right, wavelength is distance and frequency is just 1/time. So distance over time. So, and then for light, of course, and other electromagnetic radiation, the speed is the speed of light, which is constant. And we even give it a letter, we give it C, the lowercase letter C for the speed of light. And the speed of light is about 3 × 10⁸ meters per second, which is rather fast. I guess depends on your opinion, but that's rather fast. So not included in this class, though, maybe you've heard of relativity, and if you've wondered about relativity. So relativity, among other things, says that the speed of light is constant. So the speed of light, this does not change. So it's always constant. So what do I mean by that? So imagine you're driving in a car and you're going 55 miles per hour in the car, and you have a baseball. So I'll just use this as my baseball. or well, fine, I'll just use my Apple Pen carrying case. I'm tossing my Apple Pen carrier case. So as I'm moving the car, so if I'm moving the car, to me, it's not moving. For you guys, as I'm moving 55 miles per hour, this looks like it's moving 55 miles an hour. So that's the whole idea with relativity. It depends on where you're at, and it's relative to what you're looking at. That's relative to that. So now instead of, and let's put some motion into it. So let's say I throw this at 5 miles an hour, right? In the car, it's moving at 5 miles an hour. You guys, the car is moving 55, this is going 5. It looks like it's moving 60 miles an hour. Makes sense? What happens if I take a flashlight and I turn on the flashlight in the car? So if I turn on the flashlight in the car, and that means that the speed of light is moving, doesn't change. Speed of light is moving at the speed of light, and you guys outside the car, let's say, oh, that looks like the speed of light plus 55 miles an hour. So the speed of the car plus the speed of light. So that's C plus 55, And the answer is no, that's not what happens. What happens is the speed stays the same, the distance also stays the same. So what changes is time. So for you in the car, you experience time ever so more slowly than the people not in the car. So that's one of the cool things about relativity, is that time changes. So
what makes feel like that speed? What you have to assume that? Right?
it's a constant. I mean, we measure it, but we don't really know why it doesn't change.
To the observer outside of the car, would it still look like it's going the speed of light?
Yes.
55?
Yes, you will observe it at the speed of light. In the car, you will observe it at 55. At the speed of light.
Will it be both though?
Yes.
Okay.
Yes. Because we're moving right now, right? We're moving around the sun at 18 miles a second. We're moving around the galaxy at like 100 miles a second, and we're expanding in the universe fast. And depending on your position on the Earth, the radial velocity changes. We're faster here than we are in like Alaska.
Mm-hmm.
So everywhere you measure the speed of light, it appears the same. So, other questions? That's outside the scope of the class, by the way. But I just think it's cool. So, there's another way to explain the relativity. So you can do it by distance as well. So for me in the car, I think I threw that a meter. For you guys outside the car, that's moving at 10 meters a second, you would think that same toss went to 11 meters in the same time period. So that's another way to explain relativity. So I tend to do it by time rather than distance, but hey, however you want to explain it. Okay. So hopefully this is an easy question for you, just to get your brains going. So if the wavelength, what is the wavelength if the frequency is 4.62 times 10 to the 14 inverse seconds? A nanometer is 1 times 10 to the minus 9 meters. So this is just your warm-up mental exercises. I've gone ahead and hinted at the answer there. So I'm doing A, 325 nanometers, B, 500, C, 650. Okay, so most people are going to, C is the right answer. You guys just need more time that aren't doing it, or are you stuck somewhere? Okay. Sorry, I get bored fast. So this is the way you solve it. You solve for wavelength, and then you multiply by a billion for a billion nanometers to a meter. Questions with that? Okay. Next thing we'll talk about is the electromagnetic spectrum. So let's look at this. Here on the far left, you have long wavelength and low frequency. And on the far right, you have short wavelength and high frequency. So I'll start out by talking about the low wavelength, and start off with radio waves. And so the electromagnetic radiation has different interactions with matter. And I am also a spectroscopist, so meaning I study the interaction between, well, I guess I don't anymore per se, but I studied the interaction between electromagnetic radiation and matter. Spectroscopy is a very, very broad statement. So many, like a large number of scientists are in fact spectroscopists. So let's start with radio waves. What do radio waves do? They change the magnetic field of nuclei. So the magnetic field of nuclei are altered by radio waves. So a couple applications for radio waves are radio. So that is what carries the signal, AM and FM. So AM is amplitude modulation and FM is frequency modulation. You can also see television has that. We use radio waves quite a bit to look at, to transfer information. So beam information that way. Amplitude modulation, AM radio works by changing the amplitude, carries a signal that way. FM, you have the frequency changes, and that carries the signal, and then you turn on your radio in your car and you listen to the music or whatever it is, or whoever's talking. So another application of radio waves are MRIs. If you've ever heard of an MRI, that stands for magnetic resonance imaging. So what it used to be called was nuclear magnetic resonance imaging. And the word nuclear scared a lot of people, and they didn't want to get their nuclear magnetic resonance images. So do you know how they dealt with the nervous patients? Got rid of the word nuclear, yes. So now we just call them MRIs. They're not NMRIs, they're just MRIs. So here is an MRI image of me. This is my lower back. So a while back, I injured my back. Oh, it's a little alliteration there. So this is my sacrum. So you can see I'm actually not a robot. So this is not the Terminator teaching you. Here's my sacrum. Here is my L5 vertebrae. Here's my L4, L3, L2. That's, lumbar is L. And you can probably tell right away, these two discs look different than these discs. And this one has this white thing poking out. This is known as degenerative disc disease, and this is known as a protrusion. And this means that a part of my disc ruptured and was sticking into my spinal cord. And I can tell you, it's not a very pleasant feeling. So right now, I'm fine. Right? And actually, degenerative disc disease is very common, and it just, the doctor told me over time my immune system would cut this off and then it would be fine. But why go through another expensive MRI when you can move around fine? Just over time, your body heals itself, right? So if I took the MRI again, these would probably still be dark colored, but this would be gone. So, and how does an MRI work? Well, it looks where your hydrogen atoms are at. So if you've ever been in an MRI before, they're loud. So am I the only one that's had an MRI? Yeah, okay. What do you remember?
Oh, I remember, okay, so I was in middle school and I really liked bicycling in the summer and they're like, oh, what music do you want to listen to next to that? And she put this really weird, like loud rock music in the air and I was like, it was really cool. I can still hear the thing and I have no idea what's playing and you can't move. And it like fell out of my ear, I couldn't fix it.
Oh yeah.
Horrible.
What did it sound like? The MRI, yeah. I know they gave you lots of music.
Big sound, it was just so loud and I was just like so miserable and I was like, I'm listen to this.
Yeah.
Because like this old lady didn't know what to do.
Yeah, because you're stuck in the machine. They're not gonna stop it. They're not gonna stop it to. Yeah. What I remember hearing was ka-chunk, 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 brr, brr, ka-chunk, ka-chunk, brr. So what they do, I mean, you're lying down and they take magnets and they move the magnets, like ka-chunk, ka-chunk, they're just moving magnets. And then these are really strong magnets and they align your hydrogen atoms, the magnetic field. So we haven't talked about like spin up, spin down, but a hydrogen atom is just a proton and it aligns the magnetic field of the proton to wherever the magnets are. And then they blast you with radio waves. And the radio waves then go and they change the magnetic field, they excite it. And then when the protons settle back down, they emit radio waves, and that's what they're actually detecting, are the radio waves coming off from the hydrogen atoms. And they do it at different frequencies as well. And from that, they can tell by the number of hydrogen atoms and the type of magnetic field they give off, well, radio waves, which is tied to the magnetic field. They can tell if it is nerve tissue, whatever, cartilage, bone, blood, all this stuff. So they can tell you, and they just basically make a bunch of, like, they cut you into slices and they make a 3D image from all that. And so this is one of those 3D images. Yeah.
How is it different from an X-ray?
X-rays, we'll talk about X-rays later. X-rays are really high energy. You can get a lot of information from X-rays as well. X-rays more or less work then by density. So, similar to MRIs, although MRIs are a little bit better information, you can use contrast agents. So for MRIs, they typically use, so I think either a silicon compound or they inject something. I've never had it done. I forget what the contrast.
X-rays?
X-rays, yeah, they use iodine and barium.
Okay.
So really big, heavy elements.
Yeah.
So generally speaking, you get most of the same information from an X-ray than you can from an MRI, but you get more you can get more information and more detailed information from MRIs. So they're better, they're safer, and they're more expensive. So X-rays, you can get an X-ray just plain old, or like whatever body part, X-rays, film. That's when we can do it or you can do a CT scan. That's a I forget what the CT stands for. I think it's something like topography. I think the T is topography. I'm sure Google can tell us. Does anybody know what a CT stands for? What does a CT stand for? Okay, there we go. Yeah, so it looks at your density, and it backtracks, your where you're dense and where you're not, and from that it slices you up, and you can see, you can image then what you look like on the inside. So that's an X-ray, but we'll get to X-rays in a little bit. So that's radio waves. Let's scooch up a little bit in energy. So what microwaves do, microwaves make molecules rotate. So I mentioned more about temperature. Temperature is average translational kinetic energy. So things move around. So water molecules move around. This is temperature. And then this is rotation. So microwave ovens, if you remember, work by making water rotate. And so when you have water rotating, you heat it up, and then they collide. So in a microwave oven, you excite them rotationally, and then by molecular collision, it turns the rotation into translational energy or temperature. So, and another factoid we talked about before, at absolute zero, microwaves will not increase the temperature because there's no translational motion, there's no collisions. But it's very rare to get absolute zero, of course. It's very hard to attain.
Who've ever done it?
Debatable. They've gotten to essentially absolute zero, and they've also formed something called a Bose-Einstein condensate using ruthenium atoms in the University of Colorado. So that's above and beyond this class, but it seems like we have, or at least very close to it. So
It won't end the universe or anything.
no motion. No motion is not going to end the universe, and energy always goes from high energy to low energy, so it's not going to do anything in that regards. So there's not going to be any negative heat capacity. Negative heat capacity doesn't exist because of second law of thermo, which is probability. So no, it's fine. And a Bose-Einstein condensate, no, it's not going to, at least not at the level that they have. You can look up superconductors. They think that there might be a Bose-Einstein condensate with that. Do you know what that is?
Superconductor?
The Bose-Einstein condensate?
I've heard of the Higgs boson particle.
A Higgs boson. Okay. That's something different. That's what we think is the reason why mass exists. But that's, yeah. What's that?
Way above the scope of this class.
Yeah, way above the scope of the class. It's really testing the limit of what I understand as well. So we'll talk a little bit about bosons and fermions next chapter. Actually, I guess we'll talk about it on Monday, but a prelude to electronic structure. So microwaves make things rotate, and the inventor of the microwave oven actually was a technician that was working around radar. So radar, if you know, for using positional stuff, radar, although the acronym, I don't know what the acronym for radar is, but R is supposed to be radio waves. They really use microwaves. They don't use radio waves for radar. And the technician working on the radar had chocolate in his pockets. So as he was working on the radar, the chocolate in his pockets melted. So he thought, oh, this might be a good way to make an oven. So actually that guy went ahead and he invented the microwave oven. They were really expensive back then, but now they're a lot cheaper, right? You can buy one for like $40 at Walmart or something. But if you must know for microwaves though, the way that it makes it in microwaves, they take magnets and they spin them around each other. So if you throw a metal in a microwave, it sparks. It's not from the microwave, it's from the magnetic field from the rotating magnets. It induces a current in the metal. So microwaves just make things rotate. But like I said, a microwave oven generates it through magnetism. But so microwaves makes things rotate, and that's where radar is. We also use microwaves for our cell phones. So cell phones use microwaves for communication, as does Bluetooth. So all this communication going on here is done in the realm of microwaves. Yes?
As long as it's not on the other end of the spectrum, it shouldn't harm us.
Yes. So you brought my next point. Yes. There was some worry about cell phones causing brain cancer. And nowadays, of course, we don't talk on phones anymore, except in the rare occasion we just, text, or something like that, or play games. So, and I always thought that was funny because, the solution was for people that are worried about cell phone, the microwave radiation from cell phone. The point was to use a Bluetooth headset. And what do you think a Bluetooth headset uses? It uses microwaves. Now, instead of one, you have two, right? So I take my microwave emitter and I put it close to my gonads, and then I put one next to my brain, and I'm supposed to feel safer, right? So, and what maybe perhaps you've alluded to, we'll talk about later, is something called the photoelectric effect. So electrons are bound by things, or electrons are bound into atoms and molecules, and there has to be enough energy to break them loose. So it doesn't matter if you have electrons and you hit them with microwaves, you hit them with all the microwaves you want. They're not going to eject. I mean, maybe if you heat up the surroundings by temperature, then it ejects. But from the radiation itself, it will not rip electrons off. So why does that matter? Well, when you get to ultraviolet, X-ray, and gamma ray, this is known as ionizing radiation. So what does ionizing radiation do? Celebrity Jeopardy question. What would ionizing, yes?
Make ions?
Yes, it makes ions. And how does one make ions?
Get rid of electrons.
Yeah, get rid or add, but yeah, get rid of electrons. It's making ions. These have enough energy to kick off electrons, whereas these do not. So from that, you're not going to cause cellular damage from radiation from that. I mean, yeah, you can do it by temperature because microwaves do heat things up, but you're not going to create cell mutations through that process. And well, by temperature, you could, unlikely, but radiation, maybe. Radiation works, and mutation from radiation works by the radiation damaging a cell's DNA. And then DNA is double-stranded, right? So we have the backup copy. If your body repairs it incorrectly, then a mutation can occur. And cancer is a specific mutation that causes the cells to grow out of control. So cancer, most cancers at least, well, I guess not all cancers are going to be like that. They have the mutations. And but moral of the story is, for right now, microwaves cannot give you cancer. So let's creep up to a little higher energy, and we have infrared. So listen to the words. And so science, a lot of times the definitions, the words themselves are defined. Infrared, so less than red. And let me jump to visible. Red is low energy, long wavelength. Violet is high energy, low wavelength, high frequency. So infrared, infra means less than red. Ultraviolet, beyond violet. So infrared, less than red. Infrared light, what infrared light does is it causes molecules to rotate. Vibrate. Rotate is microwaves. Infrared is vibrate, means so if it's easier with, use a water example. So oxygen, hydrogen, hydrogen. If you heat up water, it can bend. So it can bend this way. This is called a bending mode. These are basically the same thing. These are bending modes. You can have a symmetric stretch. You can have an asymmetric stretch. So it makes the molecules dance. It makes them vibrate, and they can rotate too. So that's what really happening to molecules. They're vibrating, rotating, moving around. So lots of crazy things going on. And infrared light makes molecules vibrate. And we perceive infrared light, among other things, as heat, right? So when we feel infrared light, you can go up to a fire, and you feel the fire, you feel the heat on your hands. What that infrared light is doing is it's making the molecules in your body vibrate. And then again, just like the rotation. So if something is vibrating and it hits something else, ding, right? Vibrationally excited and hits something else, it turns that vibration into translational energy, which is temperature. So that's what it does. What?
So like normal ovens are infrared ovens?
Yes.
Okay.
Yeah. I'm speaking in terms of the electromagnetic spectrum. Heat transfer can happen by radiation, and I'm describing it by radiation. It can happen by convection or conduction as well. Convection is it's going to be molecular collision because you have movement of gases, and then by molecular collision, the high temperature will transfer. It also conducts through a material. It can conduct through the material as well, the vibrations and temperature. So, okay, then infrared. Some other things, infrared light can be a little dangerous because our eyes actually do focus it. Ultraviolet, our eyes don't focus. So if you ever work with infrared light, you got to be careful because infrared light is invisible to humans, but it can really damage your retinas. So, and for me, myself, and let's go into visible light. I can see down, and most humans can too. I can see down to about 800 nanometers. And 800 nanometers looks like this kind of dark brick red is the way I would describe it. Like I don't know if you had Crayola crayons, if that's, did you have that growing up? I had that growing up, a big box of crayons and all the colors in it. Like I would describe like light around 800 nanometers as like brick red and dark brick red. It's hard to see, but most humans can see it. And then of course we go through the spectrum. Red and Newton did this. He wanted to have a color I guess he liked music, so he wanted to have indigo as a color, but red, orange, yellow, green, blue, indigo, violet. And if you must know, indigo, it's this color. Jeans, like blue jeans, are dyed using indigo. So this is, and I would just call it blue, but it was just kind of thrown in there. But thank you, Newton, for other things, of course. But red light is low energy, violet light is high energy, and something about us as humans. So this is how we perceive light. So visible light. And this is just a simple graph here. And the y-axis is intensity and x-axis is wavelength. And we have two different types of cells in our eyes. We have rods and we have cones. So rods deal with temperature, just intensity of light, and cones deal with color. Cones are less photosynthesis sensitive, but they carry with them the color information. So, and most humans have three. Some have 0, 1, or 2, and some even have 4. So a 4 person and a 4 cone person is known as a tetrachrome. So I think manna shrimp have 11. So we're not the best as far as that. But as far as senses, in my own personal opinion, humans are the best at vision. So you can argue that eagles and other birds of prey have really good vision. They're good at focusing down on small points. And the other thing with eagles and other raptors, they've got tiny brains. Well, tiny compared to humans. So we humans, we have the whole occipital lobe of our brain geared towards interpreting vision. So even though we may not see as sharply as eagles, and we don't have the number of cones as manna shrimp do, we've got the big brains to interpret the colors. And we see better than dogs and cats and that kind of stuff. Certainly better than pandas. Pandas are terrible at vision. They can't really see very far to them at all, yeah.
Can those other animals see a broader spectrum of light?
Certain insects can see into the ultraviolet. So, and maybe a little bit for some land predators, because certain urine give off ultraviolet, or they absorb in the ultraviolet. So some of them can see slightly different, but in general, not, in my opinion, not as well as humans. So, but of course, I mean, animals' main thing is to find food and mates, right? So that's what consumes. I mean, certainly humans are not guilty of this at all, right? But that's what consumes most animals' brains and thought processes. So, okay, so us humans, we have, or most humans have 3 photosensitive cells. We see 3 colors today. We see 3 colors, and the colors that we see are red, green, and blue. So, and the intensity is listed as such. The color we see the best is green.
Money. Okay.
And money, yeah, well. Like, you ever seen the fluorescent green shirts? You know, like people, sometimes construction workers wear, like the vests that people wear. And like, you're like, man, I can't hear you. Like, your shirt's too loud. It's just because we perceive that color very strongly. And that's also, they used to paint fire trucks red. Now they paint them green because we see them better. Surprise, surprise. And the other big shock is the color we see the best is also the strongest sensitive, the highest wavelength that's coming from the sun. So our sun actually peaks at green. So we say the sun is yellow. Well, the sun's white, but as a star, it's a green star. So its maximum wavelength is in the green spectrum. So, but so what about, so red, green, and blue? What about yellow? What about orange? You know, what about those colors? Our brains just interprets the different intensity of these 3 colors as the different colors. So when you look at a color, you're getting that your brain's getting all this information, and then your brain just interprets it as such. And notice I'm always using the word violet and not the word purple. Does anybody know the difference between purple and violet? How do you make purple? If you want to make purple paint, what 2 colors would I mix? Red and blue. Purple is red plus blue. Violet is a wavelength of light that's at about 400 nanometers. We humans cannot tell the difference. So because our red cell, our red cone, actually has a little bit of absorption in the blue. So it's intense, mostly intense around red, but it has a little bit of intensity around blue. So for a human, if you gave a human red and blue light together, we could not tell the difference between red plus blue and violet. So if it looks the same to you, it just shows you that you are not a machine. You are, well, at least you're not you're a biological machine, at least a human one. So that's violet and purple. So if you ever wondered what the difference was. So having some more questions? All right, moving on to the ionizing radiation part. And as aforementioned, ionizing radiation creates ions. And ionizing radiation is also dangerous. So ultraviolet, sometimes shortened to UV, is ionizing radiation. And of course, well, there's a couple types. I mean, if you want to call them colors of sorts, the low wavelength, I'm sorry, well, the longer wavelength ones of ultraviolet is UVA and then UVB, UVC, at least on the short end of the ultraviolet spectrum. UVA radiation is the primary cause of wrinkles. So what a wrinkle is, you have the different layers of skin. If you have scarring on the dermal layers of skin, the epidermis, the top part of skin, will just form over that scarred region. And you can scar the skin in a couple ways. You can do it by repetitive motion. I mean, so like I know I have a wrinkle up here in the front of my forehead, but that's just the way that the contours of my skin and face are. So, but like you can kind of like when you see an old person, you can kind of say like that person smiled a lot, or that person has a forever frowny face. You can tell by the wrinkles, right? So if they're really happy people, the wrinkles up here, and the frowny face people with the wrinkles down here, right? So repetitive motion can do it too. But the primary cause is UVA radiation. The UVA radiation penetrates through and scars your dermal layers over repeated, just ionizes over time and causes damage. Then UVB UVB is, well, it's important and it's dangerous to us humans. So UVB stimulates your melanocytes and your cells to release melanin. And that's what makes us tan. So at least for me, although I just kind of turn a different shade of pink a lot of times. So I'm actually, this is tan for me, believe it or not. But like your melanocytes release melanin, make your skin darker. That's how you tan. Can also cause sunburns, can also cause carcinoma, melanoma. So UV light can give you cancer, specifically skin cancer, right? And so me, with my very light skin, I do get checked. That's why I was actually thinking about you guys. I was talking about my dermatologist. I had my yearly checkup. I get checked for cancer every year. And that's when my dermatologist told me I got, the rash behind my mask. But anyways, but UVB light is also important for us. So us humans, we are slightly photosynthetic. We make the precursor for vitamin D, calciferol, from cholesterol using UVB radiation. So UVB can give us suntans, it can help us make vitamin D, and it can also give us cancer. So it's like one of those moderation arguments, right? Too much is bad, too little is bad. Well, I guess you can survive without UVB. You have to eat something like mushrooms. You have to get in your diet to get the vitamin D. But we need vitamin D for our bones. It helps give our bones structure. So, and UVC going on ultraviolet light, C, it's just absorbed by the atmosphere. It doesn't really do that much. And anything but like other parts of ultraviolet light are important, but for us here on Earth, the atmosphere just absorbs it, so it's not a big deal. We can use it in spectroscopy. You can use ultraviolet light, getting closer to the X-ray and the spectrum. You can use it to you rip off electrons. Oh, I didn't tell you what visible light did. So radio waves change the nuclear magnetic field of nuclei. Microwaves work by rotating, infrared by vibrating. The visible light works by causing electrons to jump up and down in energy. So, and we'll talk about this much more in depth. The electrons jumping up and down in energy come from visible light. And ultraviolet light can cause big jumps in energy, but they can also ionize. And they ionize the surface electrons. So ultraviolet B radiation will give you skin cancer. It won't give you bone cancer. So I guess it could if you get a malignant tumor and it spreads to your bones, but the direct cause of it would not be from the ultraviolet light. But moving on then to X-rays. So what X-rays do, ultraviolet light deal with and rip off energy or electrons on the surface of atoms. X-rays go further down into the core. Well, not the valence. Valence is outside. That'd be ultraviolet light. Core is more bound on the inside. X-rays knock out core electrons. X-rays also knock out surface electrons too. So X-rays can give you skin cancer, but they can also give you bone cancer. But in general, radiation, cancer is actually a really rare effect. What radiation, like when I say I mean ionizing radiation. What ionizing radiation does, it mostly just causes damage, right? If I get sunburned, it just hurts. It's a burn, right? It's a radiation burn. So, and you get hit by a bunch of X-rays, your body, like radiation sickness, it's just, your body is just being torn apart and by a molecular level. So I've never had radiation sickness, thank God. But if you ever seen the show Chernobyl, right? You see some people there with radiation sickness. It's just, you're just being beat up but X-rays, like I said, can cause skin cancer. Dentists, people always hated dentists, right? I'm never like, yes, dentist day, but I mean, they had X-rays back then too. And the dentist used to stick, usually was stick his fingers in the patient's mouth. And usually dentists had like really ugly looking hands. from the repeated use of the X-ray. So that's among the other things. Dentists like, you're a dentist, look at your hands, kind of thing. So allegedly, Glenn Seaborg, he's a scientist. He had apparently really manky hands from radiation as well. But that's X-rays, and then moving on to gamma rays. So we'll learn a bit about electrons coming up. Gamma rays deal with energy transitions for protons and neutrons. And the energy levels of protons and neutrons are just like electrons, but they're much higher in energy, and gamma rays deal with that. Of course, gamma rays are ionizing radiation, so gamma rays are really hard to stop. To stop a gamma ray, you usually need about a foot of lead or about 10 feet of concrete to stop gamma rays properly. So they're really hard to stop. X-rays you can stop with a little bit of lead. Like if you ever seen if you ever go to get an X-ray, the tech usually sits behind the X-ray glass, the lead glass. So I remember, I'm a weird patient, by the way. I remember I was getting an X-ray one time, and I went up to the window. I started like flicking it with my fingernail, and the person there was like, "What are you doing?" I was like, "Oh, it's lead glass. It's lead crystal." Like, yeah, that's lead crystal. So yeah.
Do X-rays, is that what causes you to taste metal? Or was that gamma rays?
That probably, in my opinion, it was cesium.
Okay.
So it was probably actually cesium metal in the air. So, other questions? Okay, so and gamma rays also deal with nuclear transitions. So you get them from nuclear transitions. Even further, if you want to go up higher in energy, you have cosmic rays, and those are caused by like astronomical events. So you can even have higher energy than gamma rays. So, and those can be very damaging, but cosmic rays are coming through all the time. So, how we doing? Sorry, questions? Okay. So more wave stuff. So maybe you've heard of in phase or out of phase, or even resonance. So when you have two waves that are in phase with each other, so look at the amplitudes. When they're in phase, they constructively interfere. If you have waves out of phase, so you can see the crest and the trough align, you get a big wave. Here, where there is a crest, there's a trough, and vice versa. These cancel each other out. And here is also the different types of behavior. So waves diffract. So imagine you have an ocean wave coming towards like a wall, and you have a hole in the wall. What happens when the ocean wave crashes to this seawall? Well, you get this diffractive wave pattern coming out of it. And instead of waves, say that I have the same idea, but I have a hole and I'm shooting golf balls. Say I'm like practicing my golf swings and I'm shooting golf balls. What's going to happen? Well, the golf balls that hit the wall stop. The ones that go through, go through. Right? Surprise, surprise. All the interesting things you hear about in chemistry class. So let's talk about electrons. Electrons are weird. Oh, no, I guess we're talking about light for now. So we're not going to get to, well, when we talk about electrons can behave kind of like a wave and a particle. We'll talk about that soon. When you have a light source, light is waves. And when you have, this is known as a two-slit experiment. When a light source comes and hits the two slits, you actually get both constructive and destructive interference. So kind of like, have you ever taken, like, have you ever been in a lake and you were thrown like two rocks into the water and then observed the ripple patterns? Am I the only one that has done that one? Yeah, okay, you've done that. So a couple of people have. You'll see constructive and destructive interference. Same thing with light. If you take light and you mix it together, you have constructive and destructive interference, and you get a pattern. And it's actually, it peaks around the middle for the two-slit experiment, but it dies as you go further and further away. Dies down. It decays, I guess is a better way to describe it. And okay, I forgot about this. Yeah. The photoelectric effect. So actually, this is where Einstein got his Nobel Prize. So I just sent out an email. I think was it last week that's showing you the Nobel Prizes, or was it the week before? I forgot. But last week, yeah. Nobel Prize is pretty much considered to be the highest award you can get, at least in science. And and Einstein is a Nobel laureate. He didn't get it for relativity, and but what they got it for was a photoelectric effect. I mean, not surprisingly, I mean, the Nobel Prizes are very, very political, and they could never give Einstein a Nobel Prize for relativity, even though that's his greatest accomplishment. The reason is because it would have pissed off the English. Because so for us, like Einstein has always been popular in the United States. I mean, I was in Lahaina this weekend and I saw a picture, an image of Einstein with a ukulele, right? So Einstein is cool for us. But in Europe in the 1940s, to the English, he was a German. And the English and the Germans didn't get along at that point in time, right? And and not only that, this German person claimed to understand the universe better than Isaac Newton. And you do not talk badly about Isaac Newton when you were in England. The Germans, he was a Jew. And they didn't care for the Jews too much.
Einstein?
Yeah, he was Jewish. So what did he do? He moved to America. Oh, crap. Sorry about that. I had a lot of spam calls. Okay, but this is Einstein's work, photoelectric effect. What he did is he explained the phenomenon. Here's a metal surface, and if you put different wavelengths of light, actually this is usually ultraviolet, by the way, but we can't see ultraviolet, so I decided to use colors. And if you take low energy light and hit it on the metal surface, nothing happens. You do slightly higher energy light, nothing happens. You get to a point where you put light on the surface of a metal, then electrons start flying off. And then if you change the frequency or wavelength to higher energy, the electrons come off, they come off moving faster. And if you increase the amount of light, the speed does not increase, but the number of electrons that come off increases. So this idea is called the photoelectric effect. And what Einstein did with this, he said that the electrons were bound to the metal by something called the binding energy. Makes sense. It's how strongly bound the electron is. And the kinetic energy of the electrons coming off was the energy of the photon minus the binding energy of the electrons. So this brought up a couple things. So at the point in time, we didn't quite understand quantum mechanics, and we didn't understand the quantum behaviors of things. So I guess I should explain what I mean by quantum. So quantum meaning discrete, meaning not continuous. So to give you an example, everything is quantized. Space-time, we live in, is what Einstein called space-time. We live in space-time. Space-time itself is quantized, meaning if you have point A and you have point B, that you have to get from point A to point B, you cross over space-time, and it's not continuous. You only exist in certain packets. So because there's a simple proof for this, to go from one point to the other, if there is an infinite number of points, go from here to here. If there's an infinite number of points, that means, and every time you move distance, it takes a little bit of time. It would take infinite time to move an infinite number of points. So because of that, that means that the universe only exists in specific points. And that is known as the Planck length, actually. So that is space-time itself is quantized, meaning it only exists in little tiny packets of existence. Maybe you've anyone heard of Zeno's paradox before? So, as you know, this paradox is, I'm going to step half this is the door. Half the distance, half the distance, half the distance. I'm never going to reach the door, right? If I keep on going half the distance to the door. And the answer is wrong, because it's not continuous. Eventually, you will be, one quanta away from the door, and you can't go half the distance. So it's just like atoms. Atoms are also discrete, right? If I take a carbon rod and I break it in half, and take that and break it in half, take that and break it in half, I can't keep on going forever. I eventually reach an atom, right? So same thing with space-time. You go half a distance, eventually you get to the equivalent of an atom, right? The fundamental unit of space, and that's what we call the Planck length. So, which is another interesting thing, is it will never be experimentally determined, because we can only by our resolution, we can think we reach it, but we never may actually reach it. And we're not even close to that resolution yet. So that's kind of cool. I like these things, talking about it. It's kind of cool. And with Einstein, they were talking about, is quantum actually a real thing? And among other things, this started to prove that light was in fact quantized. And we have this word photon. So the photon is like an atom. It's the ultimate particle, and I'm using the word particle to describe light, ultimate particle of light. And wait a second, you just told us light is a wave, but light, and we'll find out later, electrons, light and electrons have both particle-like and wave-like behavior. And in fact, if you observe it as a particle, it behaves like a particle. If you observe it like a wave, it behaves like a wave. So, and there's this really cool, I'll have to bring this up. I should have done this before class. There's a meme that shows this, and I thought it was funny. Do I have this? Oh, no, that's a different one. Where is my meme?
Where's my meme?
Ha, found it. Oh, where'd it go? Where's my meme?
Like what that in James thing.
Yeah, there we go. So this is like under super nerdy jokes. If you take light and you observe it like a wave, it behaves like a wave. But if you take light, and this makes more sense to electrons, if you try to observe it like a particle, it behaves like a particle. So this is a two-slit experiment, and you have the interference pattern when it's wave-like, and you have the just particle-like behavior when you try to observe photons or electrons where their position is. I got a couple memes. Here's another one. You shall not pass. Okay, I'll bring that meme up next time too. Oh,
Teacher memes.
yes, teacher memes. It's where I get all my best material. It's better than my interpretive dances, I suppose. Okay, so, but I know, sorry, I'm giving you some of the history of that, but I think it's kind of cool. Oh, and the equations, the way they work. So the energy of a photon, and so the energy of a photon is equal to H. H is Planck's constant times the frequency. And if you remember, the speed of light is it's wavelength times frequency. So you can also have the energy of a photon be H times the speed of light divided by the wavelength. And H, Planck's constant, is 6.626 times 10 to the minus 34 units joules times second. So I remember when I was in college, they had something called the nerd test. I haven't seen this passed around before. Maybe it's, I don't know if it was just and engineering students, but they gave you a sheet of paper and say, how many constants do you know? And you would get points for how many constants you knew and how many digits you knew, like things like pi and Euler's number, for instance, how many digits you know down to. I don't know E very well. It's like 2.9 or something like that. But pi I know well, 3.14159.256. That's as far as I know. Yeah.
If you go on Google and you like click on pi, there's like a little mini thing you can do where it like highlights the numbers on the calculator and you follow it and you go to the next digit and then keep going.
Oh, okay, cool.
Yeah.
Those of us with more time on our hands like to study photon energies. And how are we doing? Speaking of time, we have 4 minutes left. Oh, crud. Because this is probably, and it's the last topic too. I don't know if I'll have time to finish this. I may as well start and I'll recap it next time. So nitrogen gas laser has a pulse wavelength of 337 nanometers, contains 3.83 millijoules of energy. How many photons does it contain? So, okay, so this is using this idea here with the energy is h nu. And another fun chemistry joke, if you must know, you ask someone what's new, and there's two answers to what's new, GNU. You can say nu is E over H. Nu can also be C over lambda. So if you ever know, ask someone what's new, you've got two answers for that person, huh? All right. Lame chemistry joke. I'll stick to teacher memes, okay? All right, so how do you solve this problem? And let me make an analog to something in our everyday life. If you have $20, how many $1 candy bars can you buy? The answer is 20. Surprise, surprise. So I had $20. How many 50-cent candy bars could I buy? Or maybe healthy, even though it's cheaper. Apples. We'll have apples. If I have $20, how many 50-cent apples can I buy? So 40, right? You have your number, you have your principal, well, you have your cost. Well, I should say, you have your principal, the amount of money you have divided by your price will tell you the number, right? So if you have $20 and apples cost 50 cents a piece, that means you get 20 divided by 0.5 or 40 apples, right? Same idea with photons. So instead of principal, we have energy, the total energy, and then divide by the energy per photon. And if you look at the if you look at the units, energy divided by energy divided by photon, the 1 over photon is a photon. So you would do this by 3.83 times 10 to the minus 3 joules of energy divided by the energy per photon. And as mentioned before, energy to photon is going to be hc over lambda. So you have h 6.626 times 10 to the minus 34 joules seconds. Speed of light, 3 times 10 to the 8th meters per second. And then wavelength is 337 times 10 to the minus 9 meters. So nano means 10 to the minus 9. And then you do all that and you get the answer. This is where we'll pick up. I got 1 minute left. So I'm going to go ahead and stop here. Oh, and perfect time too with my shut up alarm. So I'll revisit this on Monday. So anybody have any last minute questions? Nope. Okay. Time to